In today's class, we will be solving a few problem sums based on square, square root, cube and cube root, which are of level 1. In the first question, we need to find the cube root value of some number where we have in the numerator a decimal number and in the denominator we have integer. So what we will do in the first step is, first we will convert the decimal number into its equivalent integer, and then we will see how we can find the cube root value. To make this 3.43, this decimal number, into an integer, what we have to do is, after decimal point we have two digits, so we have to multiply this decimal number by 100. So since we have multiplied in the numerator, so similarly we need to multiply the number that we have in the denominator by the same value, which is 100. So after multiplication, it will be 343 divided by 1000. Now what we have to do, we have to see whether 343 and 1000 is a perfect cube or not. 343 is a perfect cube of 7. So it can be written as cube of 7, and 1000 is a perfect cube of 10. So it can be further written as, now it will be 3 multiplied by 7 divided by 10, then cube, and we have, or we need to find this cube root. So it will be multiplied by 1/3. So 3 will cancel each other, and finally it will be 3 multiplied by 7 divided by 10. So it will be 21 divided by 10, or it will be 2.1. Next question says that what is the cube root of a perfect even cube and what is the cube root of a perfect odd cube. Now we have to answer whether that cube root finally will be an even number or odd number. Now 8, which is an even number, and that we know that it is a perfect even cube or perfect cube, and this is a cube of 2. Now similarly, if we take 64, 64 is also an even number, so that can be written as cube of 4. So this is also a perfect cube, perfect even cube. Similarly, 1000 we know that will be cube of 10. So what we can see all in these examples, that 8 is a perfect even cube, and that is a cube of an even number. Similarly, 64 also, which itself is an even number and perfect even cube, and that is a cube of an even number. Similarly, 1000 also, which is an even number, which is a perfect even cube, and that is also cube of an even number. So our answer is that the cube root of a perfect even cube will be always an even number. Similarly, if we take example of say 27, 27 we know that is also a cube, perfect cube, and that is perfect odd cube. It is an odd number, and this is cube of 3. Now if we take the example of say 125, 125 is a perfect odd cube, and this is cube of 5. 5 5s are 25, and then 5 25s are 125. Similarly, the example that we have seen in the previous case, 343, 343, which is also a perfect odd cube, and that is cube of 7. So which is also an odd number. So what we can conclude here is a perfect odd cube is a cube of an odd number. So in all these examples, what we can see, that on the left side we have perfect odd cube, and on the right side we have represented all those odd numbers as cube of some other odd number. Now in the next question, what we can see here is the smallest number with which 16 should be multiplied to make it a perfect cube, and that number we need to find here. So 16, we know that that is a perfect square number. This is square of 4, and what we have to find here is the smallest number which we need to multiply with 16 so that the final number becomes a perfect cube. So that means with 4 square, with 16, if we multiply another 4, so that becomes a perfect cube, which is cube of 4. So our answer will be that with 16 we need to multiply 4, the smallest number, to make that number a perfect cube. Now why it is the smallest number? Because this will give you 16 4s are 64. Now 64, with 64, suppose if we multiply say 27, 27 is also a perfect cube. So the whole number will be a perfect cube. So here it is 16 multiplied by 4 multiplied by 27. So how much, or what number we need to multiply? 4 multiplied by 27. Similarly, with 64, suppose if we multiply say 125 also a perfect cube, and that is a cube of 5. So here 16 will be multiplied by 4 first, and then will be multiplied by 125. So finally again that number will be a perfect cube. So to make 16 a perfect cube, we can multiply any other number where two main factors will be, one of them will be 4 and the other factor will be a perfect cube. But we need to find the smallest number which we will multiply with 16 to make that a perfect cube, and that number will be only 4. Now the next question is, the square of a proper fraction is always what? Is smaller than that number or larger than that number? So proper fraction, we know when in a fraction the numerator is less than the denominator, that you have studied. So proper fraction, if we take an example, say 3 by 5. 3 by 5, and if we take the square value of that, then it will be how much? It will be 9 divided by 25. So now we have two numbers, 3 by 5 and 9 by 25. Now what we have to do, we have to make their denominator same. So we have to make like fractions. So to make them like fractions, what we have to do, the first fraction will be multiplied by 5 so that the denominator becomes 25. Now when we do that, the numerator becomes 15 and the denominator becomes 25, fine. And the other number, we have 9 divided by 25. So which one is greater? Definitely 15 divided by 25 is greater. And 15 divided by 25, what is that? This is the original number, the actual number of which we found the square value. So that means the square value of a proper fraction is always smaller than itself. The next question says, the square root of a prime number can be obtained approximately but not exactly. Is the given statement true or false? We know that 3 and 5, these two are prime numbers. So what we will do, first we will try to find the square root value of 3 and 5, and then we will see what we get. Now what we can see here, the square root of 3 is coming as 1.732050800756 and so on. That means this is a not terminating decimal and this is not a repeating decimal. Similarly, in case of 5, when we found square root of 5, what we obtained here is 2.23606797749 and so on. So again, this is a non-terminating decimal. So if it is, or if both the values, decimal values, are non-terminating decimals, then we have to approximate, otherwise we cannot write. So generally what we do, of root 3, we take the value 1.732, we approximate to that value, and for root 5 we approximate to 2.236. that means the square root of prime number can be obtained approximately but not exactly. This statement is actually true. Now in the next question, the cubes of the digits 1, 4, 5, 6, 7 are the numbers ending in the same digits 1, 4, 5, 6, 7 respectively. This is a statement. Now we have to see, or we have to say that whether that statement is true or not. Let's see. Now if we take 1, and if you take the cube value of 1, we know that will come as 1. Now if we take 4 and if we take the cube value of that, then 4 4s are 16 and then 16 4s are 64. So the units digit of 64 is again 4, and here again it is 1. Now if we take 5 and if we take the cube value, then 5 5s are 25 and 25 5s are 125. That means again at units place the digit is 5. Similarly, if we take now 6, so it will be how much? It will be 216, and at units place again the digit is 6. That means for all these cases I haven't considered 9, because we have already come to know that whether the statement will be true or not, because for 1 again at units place of the cube value, the value is 1. For 4 again the value is 4. For 5 it is 5. For 6 at a units place, in the q value the digit is 6. So definitely when we will take the q value of 9 at units place, it is going to be 9 only, because 9 and 9 it is 81. So at units place it will be 1, and when it will be multiplied by again 9 at units place, it will be 9 only. That means this statement is again true. Now in the next question, which of the following is not a perfect square? We know that a perfect square never ends at 2, 3, 7 and 8, right? Because we know the square value of 1 is 1, then for 2 it is 4, for 3 it is 9, for 4 it is 16, for 5 it is 25, for 6 it is 36. So you will never get to either of 2, 3, 7, 8 at units place in the square value. So we have to see the options. So here 4 is in the first option. At units place we have 4, that could be a square value. Now at 6 at units place we have 6, so that could be also a square value. But in the third option we have 2, so that means this option will be our option where we have to say that which of the following is not a perfect square. So when we will evaluate other three options, we may find that they may be or may not be perfect square, but the third one, since we have 2 at units place, so that will never be a perfect square. Now in the next question, the cube of the number p is 16 times the number. Then find p where p not is equal to 0 and p not is equal to -4. Okay, fine. Now cube of the number p. So cube of the number p can be represented as p cube, right? We know that format, and that is 16 times of the number. So 16 multiplied by p. Now we can simplify or solve this way, that if we take 16p on the left side, then it will be pq minus 16p, and that will be equal to 0. Now p, since that cannot be equal to 0, so we can take p as a common factor. So it will be p square minus 16, and that will be equal to 0. Now we have two choices, either p will be equal to 0 or p will be equal to, or p square minus 16 will be equal to 0. Now as per the question, p is not equal to 0, so our first option is not true. Then let's go to the second option. So p square minus 16, so that can be written as p square minus 4 square, right? Let's write that way. First, p square minus 16 can be represented as a perfect square of 4, and that is equal to 0. So it can be further factorized as p plus 4 and then p minus 4, and that is equal to 0. So again we can say that either p plus 4 will be equal to 0 or p minus 4 will be equal to 0. So from this option we will have p is equal to -4, and from here we will have p is equal to 4. Now again in the question it is given that p is not equal to -4. So this option is again not true, and this option was not true. So only option that will be true for us, that is p is equal to 4, and that is given in the first option. Now in the next question we have to answer this, that what is the least number to be subtracted from 220 so that it becomes a perfect cube. Now we have many methods to find the cube root or square root of a given number. Now since this time we need to find that what is the least number to be subtracted, so let's follow the successive subtraction method. Now since this is a question of a perfect cube, so we know that in case of successive subtraction method we follow this formula, where if we put n is equal to 1 and then other numbers, other successive numbers, then we get this number 1, 7, 19, 37 and so on. So what we have to do is, in the successive subtraction method, first we will subtract 1, this first number, from 220. So what number we will get? That will be 219. Then from 219 we will subtract 7. So accordingly the number that we will be getting in the second step, from there we will be subtracting this time 19, and then again the number that we will be getting, from that number we will be subtracting 37 and so on. and this will be our actual calculation. So from 220 first we have subtracted 1, so we have obtained 219. Then from 219 we have subtracted 7, so 212. Then from 212 the next number is 19, that then we are getting 193. Then from 193 we are subtracting 37, so 156. And then from 156 we are subtracting 61, so we are getting 95. And then from 95 the next number that we will be subtracting is 91, so finally we are getting 4. Now 4 is a number from where we cannot subtract the next number, which will be even more than 91. So this is actually kind of remainder. So in the actual number, if it was 4 less, then the remainder here, or the result of subtraction at this stage or at this step, would have been 0. Then that number would have been a perfect cube, because finally for a number to be a perfect cube, finally the result of subtraction has to be 0. But here we are getting 4, so that 4 has to be subtracted from the given number 220 to make that number a perfect cube. And this formula we need to remember always if we are following the successive subtraction method. So our answer will be 4, and the correct option is option A. Now in the next question, which is the last question of this class, we need to find the least number which must be added to 1200 so that the sum is a perfect square. Again, we know many methods of finding square root. So this time we will be following the division method. And in case of division method, we know the rule. So we will be pairing the digits from the right hand side. So it will be 0 0 will be one pair and 1 2 will be another pair. Now we will take a number whose square value will be either less than 12 or equal to 12, but 12 is not a perfect square. Next square value is 16, and before 12 the square value is 9. So here we will be taking value 3, so that the square of 3 will be 9 here, and we know that method. So here also we will be writing that 3 value, and then here the result of subtraction will be 3, and then the next two digits we will be taking here 300. Now what we will do in the next step, again we will divide this 300 by some value, by some divisor. And how to make that divisor? The quotient here, the value that we have obtained here as quotient, we will take the double value of that. So that is the rule of division method. So here we will take 6. Now we will take the next digit after 6 such a way that when we will multiply by the same value, the result of multiplication should match with this value to make that as a perfect square. But this cannot be a perfect square. In that case it will be less than 300. So if we take, say, 6 we have, now if we take suppose here 4, and now again if we multiply by the same digit, then it will be 4 4s are 16, we have 1, and then 4 6 are 24, and then 256. So 256 is less than 300. So let's now take the next digit. So here it will be 5, and then we will multiply by the same digits. So 5 5s are 25, here 5, and we will carry 2, and 5 6 are 30. So here it will be 325. 325 is more than 300, so it is exceeding that value. So what we will do here, we will go to the question. What it is asking, the least number which must be added to 1200 so that the sum is a perfect square. So this time what actually we will do, we will add some more value to 1200 so that value, the next value, will be a perfect square. So this time we will not consider 256, because if we consider that, then we will have some remainder here, and that if we subtract that remainder value from 1200, then that value will be less than 1200. But this time we want to add some value. So what we will do is, we have to consider the next value 325. So to make that 325, we need to add with 300 to 25 that value. So square value of 35 will be 1225. That means we need to add 25 with 1200 to make that a perfect square. So our correct option will be option B. So that's all about today's class. In the next class, we will be solving a few more interesting problem sums based on the same concept. Till then, stay safe and stay healthy. Thank you.